Okay, so now that we've been introduced to the notion of proper time, and we've also seen how we can use the metric to kind of measure distances in our geometry, let's now revisit this notion which I kind of briefly introduced, the notion of fall velocity. So just for reference, I'm going to keep drawing our space-time diagram in 2 dimensions for simplicity. And so I want you to now just go back and briefly recall when we explored a little bit about the metric or the geometry of this space-time. When we first introduced this thing, the line element, ds squared, and we defined it using the metric tensor. And we saw for the Minkowski metric, it has this fairly simple form which very closely resembles a Euclidean line element, apart from this minus sign here. And so we saw how this now essentially gives us 3 sort of distinct possibilities for the value of this ds squared. It can essentially be positive, negative, or 0. And we saw how the different values of this ds squared correspond to essentially different regions in this Minkowski space. If we just decide, okay, let's measure our separation or our interval from the origin point, then we could plot subsets of points in Minkowski space which are constant separation from the origin. And so we saw that there are the 3 classes that I mentioned. They're essentially all the points which have 0 space-time separation from the origin. So these 2 orange lines which I've drawn essentially represent all of the points in Minkowski space that have 0 space-time separation from the origin. And I started to call this object the light cone. We're going to see much more in this video, or essentially why we can call it the light cone and where that terminology comes from. But for now we just need to remember that this light cone effectively now separates our Minkowski space into distinct regions. There are these top and bottom regions which I started referring to as the forward and backwards light cone. We're going to see more what these mean today. But essentially in this forward and backwards light cone we had that the value of ds squared was negative. And so the curves of constant s are these hyperbolae. So this is ds squared negative. And then similarly we had for positive ds squared these other hyperbolae. Okay, so this is our Minkowski geometry or our space-time diagram, and we're going to be using it for reference when we start now talking about fall velocity. So let's start talking about fall velocity now. So first of all, in order to define a fall velocity, we're going to need a worldline. So let's remember we're drawing this reference frame. It's an observer who's stationary at this origin, and they can then view other particles that travel in this geometry essentially as having some trajectory throughout the space-time, which we would describe by a parameterised function. And as I introduced in the previous video, we use this parameter tau called proper time, which is essentially the time that this observer measures in their own reference frame. And we saw that how we can associate essentially this tau proper time. If you're just in your own reference frame, you travel along the time axis, that's your world line. The length of this world line is going to have some dtau, and then we saw how this is just equal to essentially the space-time separation. We just need this constant in here, and there's also a minus sign that's conventional, but we can see a lot more about how this definition comes into play in this video. But okay, for now let's just stick with our world line. I mentioned that we can now consider two notions of velocity essentially. We can consider our sort of familiar notion of velocity that we might have from classical mechanics, which would just be the gradient of this trajectory, or rather the tangent vector to this trajectory. That's what we might call the velocity vector in classical mechanics. But now what we need to realise is that in special relativity, the tangent vector, or essentially the tau derivative of this world line, is no longer just a spatial velocity, it's now essentially representing your velocity through space-time. And we call that the four velocity. The four is just kind of terminology coming from the fact that we usually work with a four-dimensional space-time. But for now, let's just call it the space-time velocity. So I've started drawing it here. We usually give it the name u. And all it is simply just the parameter derivative of our world line. So we can define the full velocity is now just simply d by d tau of our parameterized function that gives the world line. So that's simply how we define the full velocity. Let's now just see how we would go about computing it. Well, first of all, let me just tell you a little bit more about this x mu. Essentially, we can just represent this thing as kind of a vector valued function. Essentially, we just need to specify a parameterized function for each of our coordinates. So we're going to have some ct parameterized with tau, and then some x of tau, and so on, however many coordinates we have. So now let's just, so this specifies our world line. Now let's compute the full velocity. So I'll continue writing it just as this kind of column vector to keep things clear. So let's just now compute. We just simply need to take the parameter derivative of each of these expressions. Okay, that's fairly simple. Not too much happened yet, just simply taking the parameter derivative. But now we can identify a few interesting things. So this dt by d tau object, we're going to see a lot more about this, and it's going to be so useful. Essentially it gets its own symbol and its own name. So this dt by d tau object is known as the Lorentz factor, gamma. And we can see much more what this gamma is and how it controls things in our geometry. But for now it's just a factor, and it's this derivative of the time coordinate with respect to proper time. And now this space component of the full velocity, simply just the derivative of the space coordinate with respect to tau. Doesn't look too interesting by itself, but now if we use the chain rule to essentially rewrite this expression as, so essentially I've just used here the chain rule to rewrite dx by d tau as dx by dt, dt by d tau. And now we can identify, okay, well this thing here, this is the Lorentz factor, and this thing here, dx by dt, this is what's known as the coordinate velocity v. So this coordinate velocity now is the actual velocity that we would expect from classical mechanics. Essentially, it's how much is your x-coordinate changing with respect to time. And now we should be absolutely clear that this is a velocity that's viewed in this reference frame. That's why we refer to it as coordinate velocity. Essentially, it's just how fast you're viewed to be moving through this reference frame. And so we can see just from the form of the full velocity, essentially it's going to have a time component which is somehow dependent on this Lorentz factor, and then a space component, which also depends on this Lorentz factor, but that now contains this kind of coordinate velocity piece. So if we just quickly look back at this figure, I was drawing my 4 velocity vectors, just being the tangents to our world lines. We can now see what these two different components are. Essentially, we're going to have, pointing along the x direction, is going to be this space component, which is somehow proportional to its coordinate velocity. This is intuitively clear since this is just a one-dimensional space. We can only move in that direction or the opposite direction, and so our coordinate velocity is just going to be a vector that points plus or minus in x. So that's the space component of the full velocity, and then there's also just going to be some time component depending on what this Lorentz factor is. So essentially all we've really done is just define full velocity as the tangent vector to any world line. We've seen how we can express it in terms of the coordinate representation of that world line. And so we've identified this gamma Lorentz factor that we're going to see much more about in upcoming videos. And now we've also seen how the traditional notion of velocity, the coordinate velocity, is kind of a part of this larger full velocity. It's the space component, but it's now also being affected by this Lorentz factor. So in future videos we're going to see how these components are interconnected, and essentially this Lorentz factor is used to constrain the velocity. And we're also going to see how the overall normalization, this full velocity vector, we're going to see is always going to be constrained to have a fixed space-time length, and that's going to effectively then constrain each of these components to be, or to take a particular set of values, and we're going to see how this effectively constrains the velocities depending on where you are in this space-time diagram. So that's coming up in the next video.